Good morning, everybody. Lecture 3 for Control Systems Engineering and Industrial Control. The first week we talked about getting a differential equation for the different systems. Last week was getting the S-domain transfer function for the systems. Okay. Now we're going to look at how we model the time response of those systems. Okay. So this is looking at time response, and we're going to focus this week on first-order systems. Next week we'll look at second-order systems. Okay. But the first thing we need to do when we're modeling time response is to think about the different sorts of inputs that we might want to give when looking at time response. And the standard three inputs are the step input, the ramp input, and the pulse input. And so we're going to talk about these, talk about how we represent those different sorts of inputs, and then we'll look at the response of those systems. And so, like I said, this week we're just looking at the first-order systems, and we look at the response in the time domain of a step and a ramp. And then there's this thing called the Final Value Theorem, which is a theorem that we'll run through that allows you to find, after time has gone on for a little while, it allows you to find the final value of your system. Okay, so say that there's an error, a slight error in your system, you can look at the final value. Okay, and it's looking at, as time tends towards infinity, you'll get a steady state. Okay, and this will give you the value of your steady state. And often, with real systems, you don't necessarily get the desired values that you want. And there's various ways that control algorithms that you'll study in the course of the year that will allow you to adjust so you can get the final value that you're actually looking for. But this theorem we'll use just to find the final value as it currently stands. So let's make a start on different sorts of inputs. A step input, okay, let's assume that it looks something like this. So you've got time along the x-axis, some function in time along the y-axis, okay, and up to time equals 0, the value is 0. Then after that point, you just have a constant value of a. Okay, so this is a step input. Nice and simple. Often systems will be using step inputs in systems. You set it to a certain value, and that's what it looks like. Now, what we need to work out is the S-domain version of this function. Okay, so what we do is we use the Laplace transform equations. Okay, and so Laplace transform we always know is some function multiplied by e to the power of minus st. Okay, and so what I've done here is I've taken the integral of e to the minus st, and you end up with minus e to the minus st upon s. Okay, that's between 0 and infinity. Okay, so there's the one with infinity, there's the one with 0. Obviously this term, e to the power of minus infinity, is 0. That drops out. And e to the power of 0 is 1. So you just end up with minus e to the e over s, and so you get, a over s. Okay, so that's the for a step input, that is your input. Okay, a divided by s. So that's a step input. What about a ramp input? And oh yes, of course, if a is 1, then this is called a unit step function. Then a ramp input, okay, well that's slightly different. We've now got this additional t because it's essentially a straight line. That's the equation for a line. And so up to time 0, the function is 0. And then after time 0, you have a function of a times by t. Okay, so as time increases, the function increases linearly. Okay, and so we can do the same thing again. The equation for Laplace transforms is the integral between 0 and infinity of a t, which is our function, times by e to the minus st dt. Okay, now, unfortunately, this is not a simple integral to do. We've got to do integration by parts, so I take the a out, that's the constant. I set t to be u, okay, and e to the minus st dt is going to be dv. And so if u equals t, then du equals dt. Okay, that's easy. And then if dv is e to the minus st dt, then we know that v on its own is just going to be this e to the minus st over s, which we know is the integral for e to the minus st. And so we run through. We apply this equation, uv minus integral v du. Okay, and So A is a constant, so that's multiplied by the whole lot, and then we've got this. That's uv, and then we've got the integral of v du here. And the integral of, well, that term between 0 and infinity comes out to be 0. Okay, and then we've got a over s times by the integral between 0 and infinity. And look at this. We've seen that before. That was the unit step function. And so we have a upon s times 1 upon s. And so you get a upon s squared. And so we've got the step input was a upon s. The ramp input was a upon s squared. And again, if you have a equals 1, then you have what's known as a unit ramp input. Unit step input, unit ramp input. A pulse input. Now, a pulse is where the function in terms of time is some value a, okay, upon this t0, okay, so, and that's between 0 and this t0 time. And so here I've got t0, okay, and you can see this box here, okay, and what happens is that that area is known as a, okay. Now what you can do is you can bring t0 closer and closer and closer to zero, and this area a will obviously change shape like that. So you get, obviously this will then be a, this will then be a, and this will be a. So the area stays constant, but t0 reduces. And as that approaches 0, the pulse turns into what we know as an impulse, okay? And if a equals 1, then we have a unit pulse, if it's like something like this. Or if we're dealing with an impulse, so t0 approaches 0, then we know that as a unit impulse, okay? And the examples, because I suppose it's a little difficult to sort of understand. Steps and ramps are quite easy to understand, but impulses and pulses are a little harder. Something like physiology, the shot of a drug, obviously you can model the time that it takes for that drug to sort of travel through your system. Or in hydraulics, another example is that you've got a volume of fluid and you dump it. Okay, so obviously that's a sudden drop of fluid. And those things can be represented by impulses and pulses. And so again, so here's our function, and we can again run through the Laplace transforms. Okay, so this time instead of between 0 and infinity, we've got between 0 and t0. And there's our function a upon t0, and there's obviously for the Laplace transform, that's multiplied by e to the minus st dt. Okay, well that's all constants. We can bring them out. Okay, and that's between 0 and t0, and so you end up with this term. Okay, what about for an impulse as t0 approaches 0? Well, what we can do is we can take this term and then do the limit as t0 goes to 0. And so what we do is we've got this function, we bung it in here. Again, a is a constant, so we don't need to worry too much about that. And this is the limit as t0 goes to 0 of all of this term, okay, with st on the bottom. Now, the issue with this is that as t0 goes to 0, just looking at this on its own, this term will go to 0, which obviously means that the whole thing goes to infinity. But that's not true, okay? That can't be the case. And so we use what's called L'Hopital's rule, which says that if you've got a limit that goes to 0, that goes to 0 or to infinity, okay, what you can do is take the derivative of the top and the derivative of the bottom, and then do the limit, and you end up with a value. Okay, so what we do is we do the limit. Okay, derivative of the top, well, obviously the derivative of 1 is 0, and the derivative of this is going to be minus e to the minus st. Okay, and we bring the s obviously down from there as well. So we get minus s e to the minus st, and obviously a minus is a plus. And then on the bottom, the derivative of this with respect to t0 is going to be just s. The s's cancel, and so we've got the limit as e to the minus st. If we stick 0 in here, then obviously that term turns into 1, and so you just got a multiplied by 1, which is a. Okay, and so for a unit, so for an impulse, the input is a. Okay, it's just a value, and if you've got a unit impulse, then the value is 1. Okay, your input is 1. And so we've got our three sorts of inputs. Like I said, this is L'Hopital's rule. unit impulse is 1. We have a step input, which we saw was A upon S. That's your input to the system. If you've got a ramp, it's A upon S squared. And then if you've got a pulse or an impulse, you have A. And then for a unit value of any of these, then you just replace A with 1. Okay, and then that will give you a unit step, and a unit ramp, and a unit impulse. And so last week we looked at what was a transfer function, and we, like I said, we introduced the idea of this block diagram, okay, where G of S is our transfer function, R of S is the input, and C of S is your output. And so now, by knowing what the input values are going to be in terms of S, and knowing what the transfer function is in terms of S, which we did last week, we can work out what the output is going to be like. Okay, so we have this system now: input, transfer function, and the output. RS is our input, and so for a step, it's going to be A upon S. For a ramp, it's going to be A upon S squared, and for an impulse, it's going to be A. So that's our value for RS. G of S depends on your system. Okay, you've got a tank, we know what the transfer function is, all those sort of things. Okay? And so, RS is the input, step input. Okay, well C of S is going to be A upon S times G of S, okay? Because we know that C is going to be R times G. Well, if R is A upon S, then we get A upon S times G, that's our step input. Okay, our ramp input, C of S times A upon S squared times G of S. Okay, this makes sense. And then, for an impulse, we're going to just have A times GS. Okay? So, this is our system. We've worked out what the inputs are going to be. Last week we looked at the transfer function, so let's see what C of S comes out to be. And then what we need to do is look at it in terms of time. Okay, because obviously in terms of S, we just get a value, okay, or some sort of function, but to actually visualize it, it's quite useful to convert that back to time. And to do that, we use inverse Laplace transform tables. Now, your tutorial sheet this week, okay, some of you may have downloaded it already, but on the front there'll be the questions, like normal, and on the back of there's the inverse Laplace transform tables. And so what the idea this week will be to work out what this is, okay, and then convert that back to the time domain to be able to visualize what's going on, okay. And that's the idea. So time response. So to determine the time response, okay, you apply the input to the transfer function, okay, as we did on the previous slide. You then simplify if it's at all possible, okay. It's quite a good idea. And then you use inverse Laplace transform tables to convert from the S domain back to the time domain, okay. Now, obviously, what you want to do when you're simplifying it is convert it into a form that's on the table. Okay, often your function won't be in the right form, and you need to do some algebraic manipulation to get it into the right form. And so let's do an example. We've got a first order system, okay, a unit step. So we've got our input is 1 upon S, and let's say our transfer function is in the standard form, gamma upon 1 plus tau S. Okay, and what I'm doing is I've multiplied the top and bottom by 1 upon tau. So I get S on its own, okay? And so I have gamma upon tau on the top, and then S plus 1 upon tau. So I've gone from this standard form to another standard form. Okay, this is the one where I know what tau is, and so I can work out various aspects of it, the transfer function, the gain. I've converted it into this form, A upon S plus A, okay? Which is another way, another form of doing it, where A is gamma upon tau and A is 1 upon tau. Okay, so there's my transfer function. There's my input. So the output is going to be those two multiplied together. Okay. The output, C of S, is 1 upon S. So there's the input multiplied by A upon S plus A. And so I get this nice nice output there. A over 1 plus S plus A. Okay. 1 upon S times S plus A. Now, the issue with this is that this function doesn't appear on Laplace transform tables generally, okay? And so we need to do a bit of manipulation to work out what we have got on Laplace transform tables. So there's our function, our output. And what we do is we use what's a technique known as partial fraction expansion. Now you should all be familiar with this. This is quite basic maths. When you've got a fraction and the denominator has two terms that you want to separate, then you use what's known as partial fraction expansion to work out what these values a0, a1 and a2 are. Okay, so you can separate the denominator of the fraction. You see here that this function here is going to be equal to some term over s plus some term over s plus a. Generally, if the denominators are different orders, okay, so there's s on the bottom, or s squared in fact in this case, and nothing on the top, then a0 will end up coming out to be 0. Okay, so a0 0, like I said, they've got different orders. And so we can say that C of s is a upon c s plus a, okay, and so that's equal to a1 over s plus a2 over s plus a, okay, and so we can, what we do now is we multiply both sides by the denominator, okay, and so if I multiply both sides by the denominator, so that's the whole denominator, okay, if I multiply this by that, okay, the s's cancel, I just end up with a1 multiplied by s plus a, okay. And on this side, okay, if I multiply that, the s plus a terms cancel, and we'll just end up with a2 times by s. This is all about finding out what those two terms are, a1 and a2 are. And so I've now got an equation down here, a1s plus a1a plus a2s, okay? And what I've done here is there's an s term in here and an s term in here, so I've taken them out. Okay, and then what you do to find out those values is that you look at the terms in terms of s and the terms that have no s in, or s to the 0. And so if I look on this side I've got a with s to the 0 in a sense, a times 1. And so obviously I know that this term is that term there is going to be 0. And I know that a is going to be equal to a1 multiplied by little a. And so I can make, so like I said, by grouping common terms, I can make this, that's true, okay, so obviously a1 is going to be big A over little a. And if I know that a1, there's no s term on the left-hand side, and so a1 plus a2 must be 0. Okay, so 0 equals a1 plus a2, and since I know this, I can plug that into this, and I find out a2 is going to be minus big A upon little a. And so now I've got values of a1 and a2, and so I can rewrite C of s in terms of two terms which are on Laplace transform tables. And so I input these values into my equation at the top, okay? I end up with these two things, so a upon little a times 1 upon s, and a upon little a times 1 upon s plus a. If you look on the Laplace transform tables, what's that? That's a unit step input, okay? And then this term is going to be some exponential. And so you look upon the tables, well, there's our input, our step input, okay, which is just a constant. And then we know that this term, okay, comes out to be some exponential e to the minus at. And so what I've done is a upon a here and a upon a here. I've taken them out. I end up with a upon a times by 1 minus e to the minus at. Okay, so this is the time response for a step input with a first order system. And it always follows this form. Okay, the time response of a step order input. And so you'll always come up with something that looks like this. Now, what does that look like in reality? What does it, let's see what's going on. Okay, well, we can use that equation to estimate the step response. Okay, so we know before that a is gamma upon tau, and a is 1 upon tau. Little a is 1 upon tau, and we can rewrite it in terms of our terms. Okay, so we end up with C of t is the gain multiplied by 1 minus e to the minus little t upon tau. Okay, so this is our time response. And let's plot some values. So when time is 0, the output's going to be 0. You stick in t equals 0 in there, you get 1 minus 1. It's got to be 0. Okay, you stick in tau for there, you get e to the minus 1. Okay, and you get this value, 0.632% of whatever your gain is. 3 torr is 95%, 5 torr is 95%, 5 torr you get to 99%, 10 torr you're almost there, okay, but it's an exponential, so in a sense you never get there. And so if we plot these values for a unit step, there's our transfer function. If I set the gain to be 1 and torr to be 1, okay, then we get this sort of response. So here's our input. The red line is our input. It's a step response from 0 to 1, okay, unit step response. And these values along here is torr. So 1 torr, we're at 63% of our input, okay. And 2 torr, okay, we're somewhere about 90%. 3 torr, 95%. You can see that 5 torr, we're almost there. 10 torr, we're even closer. And so, like I said, last week when we were looking at standard forms, we could find out, just by looking at it, what torr was. Well, you can see that now we know what torr is, we can make a judgment. All first-order systems will respond like this to a step input. And so by knowing what this is, we can say, okay, well, we know that after one time constant, okay, so let's say that was 1 second. Oh, we know that after 1 second, we're going to be 63% of the way there, okay? And we know that after 3 seconds, we're going to be 95% of the way there. And after 10 or whatever, we say that that's going to be, we're there in a sense. And what we often talk about in control is we talk about settling time, okay? Settling time is often within 95% of your final value. Okay, and so in this case, the settling time we know is 3 torr. And if torr is 1 second, then we know that our settling time is going to be 3 seconds. Okay, a 95% settling time. And so, like I said, by looking at the standard form, we have this value, which is the value of looking at, which is why we rearrange stuff to put it in standard form. And we can find out what torr is. If the gain was 1, okay, then if the gain wasn't 1, then we'd obviously have a final value up where the gain is. Okay, so if the gain was 3, it would be a 3. Our final value would be 3 in a sense. But we'll look at that in a second. So this is a standard first-order system with that. This is the response you'll always get with a first-order system. In one time constant, you will get 63% of the way to your final value. Okay, well, what about... So, yeah, like I said, the unit step will always have this form. K times 1 minus e to the minus t upon torr. And like I said, it reaches 95% of the final value after 3 time constants. 3 time constants, you'll be 95% of the way there. And the time constant, torr, must be small for a fast response, which makes sense. If I go back to the graph, okay, if torr is small, then obviously you're going to get a fast response. It's going to go up much quicker and get there. And so if you've got a torr, let's say torr is 0.5, then obviously after here, this point would be here, okay, and after 1.5, I'd be 95% of the way there. So you can see that it would shrink, well, it sort of compress this down into a smaller time. Let's say that I got 10 torr as 0.5, or torr is 0.05, then obviously within half a second, I'd be all the way there, yeah? That makes sense. And so you're just basically compressing this down as torr tends to 0. Okay, and this is known, okay, as a first-order lag. So think about the sort of system that might have this response. Like I said, let's imagine you've got a furnace, okay, it's on, but you then dump in a load of fuel. Okay, so there's our step input, and it takes the time to reach the full, heating power of that furnace, and that's the response that's going to happen. Okay, so there's a first-order system. It responds like this, and this sort of shape is called a lag because you've got this input, and there's going to be a time delay between what you get and then when you actually get it, and that's called a first-order lag. And this sort of thing, this sort of cutting the corner, can be represented by an RC circuit. And if you remember when we were in the first lecture, we talked about some electronic circuits, and we determined that a RC circuit was a first-order system. Well, that's what it's exactly doing. And so often in electronics, okay, you'll put an RC circuit in to get a nice first-order lag to cut off the corner. So that time constant must be small for a fast response, and that's called a first order lag. What about a ramp input? Well, let's use a unit ramp. The transfer function, again, I've rearranged it to put it in this sort of form, and multiplied by 1 upon s squared. Okay? And I won't go through the maths this time. It's not listed on the Laplace transform table, so again, you can, like I said, you expand it out. If you've got an s squared, you must have the 1 upon s as well. Okay, so we've got 3 terms. A naught is 0, okay, different orders. And the solution with gamma equals 1 and tau equals 1, okay, is you end up getting this as our form, okay. Like I said, I've missed out the maths. If you're particularly bored one day and you want to work it out for yourself, you can do so, okay, but I've gone straight to the solution here because often, you get it into that form, you can then go straight from that to our tables. And so for this system, for a ramp response and unit ramp and our first order system, you end up with this form as your time response. So like I said, these are sort of standard forms. You can say as first order system, I know the response for a step is going to be some value times by 1 minus e to the minus minus t upon tau. Okay, well with a ramp input, we have this t term times by the tau times by 1 minus e to the minus t of the tau. Okay, and so what if we plotted this? What did that look like? Well, there's our function, and this is what it looks like. So we've got our ramp response. That's the value in red. Okay, and what we do is we say at four times constants. Okay, we've reached a steady state where there's this constant lag of time constant tau, okay? Because obviously there's between here and here, you can see that these values are sort of diverging, okay? But after 4 tau, we can see that gap between the two is constant, and that's denoted by the time constant. So demand and response. And so with a ramp input, you'll always get this sort of shape, okay? You'll always have a lag of some degree. And obviously, the smaller your time constant, the closer that lag's going to be, or the closer you're going to be to what you demand. So as the demand increases, you get this lag, and that's denoted by your time constant. Again, showing why we put stuff in standard form, because if we know what tau is, we can automatically think about what the response is going to look like for a ramp input. Again, what about first order with an impulse? Okay, well, we know that the input's going to be 1. Rearrange the transfer function. Okay, again, you go through. There's our output. And we know that the inverse Laplace transform of this is a minus exponential. Okay, and so we end up, like I said, we've already found that in the tables. It's going to be a times e to the minus at. A being our initial value, which in this case was y upon tau. And then we have minus t upon tau as our exponential. And so you can plot that. It's quite nice and easy to plot that. Unit impulse. So there's our things. So here's our impulse. Like I said, it's an impulse, so t naught has gone to 0. It's a value of 1. And you just get this exponential that drops down. Okay? It's sort of, this is just a e to the minus value shape. Okay? And that's the standard form of a impulse. Okay, so what we've done so far is we've gone through the different types of inputs. Okay, a step input, a ramp input, and a impulse. Okay, and what we've then done is we've looked at with a standard first order system. Okay, we've rearranged it, we've applied the input, and then we've gone back to the time domain to plot the response. And often going back to the time domain will involve partial fraction expansion. Okay, which is simple sort of GCSE level algebra, but you've got to do it. And then you look up on the tables to find out what the time response will be for those standard forms. And like I said, you can often use the table as a hint to find out what you need to convert it back to. Okay. There's one problem on your sheet that's a bit tough. The standard form isn't very easy to find, and I've given you an additional inverse Laplace transform. But one you need to get, the form you need to get it into is quite complicated, but you can do it, and that will give you a response. So on the tutorial sheet, there will be some second-order systems as well. It's not all first-order systems. But like I said, it should be relatively straightforward. But we'll look at specifically next week at how second-order systems respond, because they have a unique, well, they have different properties as well, due to the additional terms in second-order systems. But this week was just first-order systems. So that's what we've done. We've looked at the response for a step input. We've looked for a response for the ramp input. And we've looked at the response for an impulse. And they will always follow these forms, okay? A step will always be something that goes up exponentially to your final value. A ramp will always lag the input, okay, as it ramps up. And an impulse will always start at this value and then drop down, okay, to 0. Now, the last thing on our contents list was the final value theorem. And like I said, the final value theorem is to find the steady state value of your system after an input of some description, be that a step, a ramp, or impulse. And this is the final value theorem. The limit as time goes to infinity of your function in terms of time is equal to the limit as s goes to 0 of s times your s domain function, okay? Which makes sense, as time goes to time goes to infinity, all your d by dt terms, the s terms, are going to go to 0, because d by dt denotes something that's changing with respect to time. Well, if time has gone to infinity, then nothing's going to be changing with respect to time. So all your s terms drop to 0. And then it's s times your function in terms of s, okay? This is the final value theorem. Don't forget this additional s term. It's not just of the function. There's an s term in here. And so an example, here's our transfer function. Okay, it's not in that standard form, but it's in a form that's quite nice to convert to the time domain. G of s. My input, well, I could call this r of s. In this case, I've called it f of s, is a step input with 3 as my a. Okay, a upon s. A is 3. So there's my input. There's my transfer function. Obviously, my output is going to be this here. That could be the C of S, okay? Okay, or F of S, or whatever I want to call it. I should have probably been a bit more consistent. Apologise about that. But I stick this into there for F of S. And so, as my function in terms of time, little x, as t goes to infinity, is the limit as s goes to 0 of s times this lot, okay? Now, if I multiply this term by s, which is here, okay, obviously that s cancels with that s. That obviously is 0, so I end up with 15 over 3. 15 over 3 is 5. So my final value is going to be 5. My gain is 5, okay, in this system. My input was 3, and I'm getting 5 as my response. Okay? That may be what I want. It may not be what I want. It depends on the system. But so with a step input, 3 upon s, my first order transfer function, I've got my gain is 5. S plus 3 is the denominator. So my tau in this case would be 1 upon 3. And my final value is going to be 5. So that is the final value theorem, this line here. That's what you need to remember. Like I said, if you want to call this C of t and this big C of s, then you can do so. In this example, I've called it x of s. Whatever, just make sure you know that this is the final value theorem. And don't forget that s term. On the tutorial sheet, there's a few examples where you'll be applying this. Okay, and it's quite simple, quite straightforward to do. So, you're lucky we're ending a little early. Today, we talked about different types of inputs. We talked about, first off, the pulse, the step, and the ramp inputs, and how they're formed in terms of the S domain. A step is A upon S, a ramp is A upon S squared, and an impulse is just A on its own. There's no S term. And to determine the time response, okay, you get the transfer function in the S domain, so you apply your input, you then go back to the time domain using inverse Laplace transforms, okay, which are on the tables which you will be provided with. You're not expected to remember them. like I said, if you're having trouble wondering what Laplace transforms are all about, and you want to read more, go to your maths notes. Okay, I think you're doing them at the moment, for some of you at least. Some of you perhaps did it last year, but it's all standard maths. And often we use partial fraction technique, okay, and then we have to get it in a form that you can use the inverse Laplace transform tables. That's ILT, inverse Laplace transform tables. Okay. So you use the partial fraction technique. It's quite good. If you're having trouble with that, is to do a bit of practice, because you'll be using it all the time. Partial fraction expansions. And as a little hint, on the exam last year, a lot of people fell over when they were doing the partial fraction expansions. They got everything else right, but they fell over when they were doing this. So it's well worth you making sure that you can handle it, okay? It's simple algebra, but you just need to make sure you're doing it correctly. Step response, ramp response, and final value theorem. Step response and ramp response, like I said, will always follow a standard form. We saw in the slides, which you can download off Blackboard, you'll see the standard form. Ramp response will follow a standard form. And then the final value theorem allows you to determine the final value for your system, depending on the input and the system. Thank you very much. See you next week.